All right, science time. We're going to talk about, what were we going to talk about? Magnets. Magnets. Let's write magnets up here. Magnetism. 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 What's a magnet?
It attracts metals and stuff.
Okay. Does it attract all metals?
No.
Okay. What metal?
Only metals that have
Okay, so you said something that's true, but Cyrus, what did you say?
I said
Only metals that have a magnetic field it attracts. That's not exactly true, because some metals can be induced to have a magnetic field. Like they don't have one if they're just sitting there. Like for instance, if we had a magnet, which if I'd been smart, I would. I guess I do have some. This has a magnetic field right now. I'm holding it. It has a magnetic field. You can't tell because it's invisible, but it does have a magnetic field. The board does not have a magnetic field right now, but this does. And so if I bring this close, then now the board is induced to have a magnetic field so that they attract. But does this work for everything? Like if I try to put it on my coffee cup, will it induce the coffee cup to have a magnetic field? No. So there's at least 3 different kinds of magnetism, right? There's this one, which is a magnet as I hold it. There's this one, which isn't a magnet right now, but if I bring a magnet close, it will attract or repel that magnet. And then there's this, which is not magnetic at all. Okay? So let's list some kinds of magnetism. And there are more than just this, but let's list some kinds of magnetism. Let me think if I can remember the word. I always call it a permanent magnet. That's kind of like the old-fashioned word for it, because this magnet is not permanent. The reason we stopped using that word is because eventually, over time, the magnetism will wear out of this, especially if it's hooked onto something or if it's not, I don't know, upgraded. What is paramagnetism? That doesn't sound right. We'll call it a permanent magnet because that's what I know it as. Permanent magnet. It's called that because it has generates its own magnetic field. It might even just be called magnetism. Doesn't sound right either, though. And then there's this idea of paramagnetism. Paramagnetism, which is where it can be a substance that can be induced. What's induced mean? This is related to the word, actually, the noun version of this is induction. There's a National Honor Society induction. You're aware of this? That people get induced into the National Honor Society. What does that mean? Almost. It's not quite the same as introduced. You also, if you're pregnant, you can be induced into labor. What might induced mean? Yeah, to make it be in that state. So a substance that can be induced to have a magnetic field. And then there's diamagnetism, which is what we call it when this is not exactly true, but at this level this will be fine. Interaction with magnets. And this all has to do with what subatomic particle? Can you guess? Because it's all part of some force. What major overarching force of the universe are we dealing with when we're talking about magnetism? Of the 4 fundamental forces, which one involves magnetism? You remember what they're called? What are the 4 fundamental forces of the universe?
push, pull.
No.
Gravity.
Gravity's one. We talked about it earlier. You can look in your notes if you want. Gravity's one. No. 4 fundamental forces of the universe. Let's write them down now, since we obviously need a little bit of a refresher. I'm going to make this so that we can see what's on the board too. The 4 fundamental forces of the universe, in order of strength, are the strong nuclear force. Do you remember these now? Strong nuclear force, weak nuclear force, electromagnetism, and gravity. When would we have talked about these before in this class? When we talked about what? When we talked about gravity. And now we're talking about which one? Probably electromagnetism. So this is it's part of electromagnetism. What is the other thing that we just learned about that the force of electromagnetism governs? So electromagnetism governs magnetism, and what other phenomenon that we just learned about? No?
Really quick, so...
Give me a second. I'm trying to ask you a question, and I want you to answer it. What other thing did we just learn about? What other science word that we just learned about? Yeah, what did you say? Not just static, but all kinds of electricity. So electromagnetism is about electricity and magnetism and how they interact. Actually, they're the same force. So what subatomic particle, which of the subatomic particles probably is generating all of this, is what I'm getting at. What subatomic particle was dealing with electricity? Electricity was the flow of electrons. Magnetism has to do with electrons too. This all has to do with electrons. In fact, generally, if an object, and I want you to write this down, this is, I wouldn't even say general, I think this is just the rule. If an object has unpaired electrons, it's one of these two. And it depends on how the electrons, how alone the electrons are, I guess, whether it's going to be one of these two. And so this will have unpaired electrons. And it's not super important that we know what that is right now because we're going to talk about electrons and what it means for electrons to be paired later on in the year when we talk about chemistry. But I want you to write it down that if it has unpaired electrons, it'll be one of these two, either a permanent magnet or paramagnetic. And then if it has only paired electrons, it's diamagnetic. And it's not, remember, it's not specifically true that there's no interaction with magnets. In fact, if it's in a strong enough magnetic field, diamagnets repel magnets, always repel. In fact, I was just reading the most diamagnetic substance is bismuth, and if it's in a strong enough magnetic field, it'll just levitate because it wants to be away from the magnets that bad. And in fact, everything that isn't one of these two is that. There's a cool experiment they did with a frog, which is made out of diamagnetic stuff. It's just a frog, like a regular old frog, and they put it in a super strong magnetic field and it levitated because it's made of stuff that's diamagnetic. Yeah, so you could do it. If they put you in a strong enough magnetic field, you would levitate. You can't be by a magnet because the stuff you're made of is diamagnetic. Colton.
So with only paired electrons, diamagnetism is the only thing there?
Yeah, yep. This one just is only, if it only has paired electrons, it's diamagnetic. So what kind of things have unpaired electrons? Well, there's lots, really. But the ones that generate their own magnetic field, the permanent magnets, are usually one of these several substances. And they are usually iron, so I'm going to put that one first. Iron. It can also be nickel or cobalt. Those three are very common. And then also I'm just going to put some rare earth metals. Most magnets that you've interacted with in your life are probably iron or nickel or some combination thereof. If you have a very strong magnet in your house, like maybe one, if you have a magnet on your fridge that, like if you try to pull it off, you can't because you're not strong enough, then it might be a rare earth magnet. Or they can make iron magnets that are that good, but generally, and these are the rare earth metals, generally they'll be made of something like neodymium or praseodymium or promethium. Not promethium because it's radioactive, but one of those two is the ones I'm familiar with, being very strong magnets. How it do? What's going on with the thing that makes it have a magnet in it? Well, so basically, let's start with what an atom looks like. So we have what's in the middle of an atom. What do we call that? Not just the neutrons, but the neutrons and the protons, which together make up the nucleus. So this is the nucleus, and it's surrounded by a cloud of electrons. So there's all electrons in here. Electrons, when they can, electrons exist in pairs. They like to be in pairs. One with a top spin and one with a bottom spin. That's what we call it with electrons. Electrons can have two spins, top or bottom, and they like to exist one with the other spin. So in a substance that only has paired electrons, all of them have a buddy. The top with the bottom, the top with the bottom. But in some substances, like iron, there are several unpaired electrons. And that's not uncommon, but in some substances, like iron, all of the atoms in a little line, because if you're dealing with a piece of iron, you're not dealing with just one atom of iron. So in some pieces of iron, all the unpaired electrons line up in the same direction, and this makes what's called a magnetic domain. So a magnetic domain is an area in a substance that all the unpaired electrons are lined up the same way. So we start with an atom. Each individual atom exhibits the electromagnetic force because of its electrons. And some of those electrons are unpaired. And if all those unpaired electrons line up, it is a magnetic domain. And then, if in a big old substance, like a magnet inside an eraser, for instance, this is much larger than an atom. There are trillions of atoms in this little eraser. And if all the magnetic domains are lined up, it would be a very strong magnet. But to make this little weak magnet, most of them are lined up. So if I go to my next biggest picture and I draw my eraser, the little magnet inside of it will have several magnetic domains, which are just areas of the magnet, and most of them will line up. Most of them will have the same north pole. Some of them will be away because it's not a very strong magnet, but most of them line up, and that makes a macro, like a big scale, magnet. So it all starts with the electrons. When the unpaired electrons line up, that makes a magnetic domain, and then if the magnetic domains line up, it makes a permanent magnet. What do we call the ends of a magnet? If I have this bar magnet here, north and south. If I draw another bar magnet next to it, let's say they're attracted. What should be here? What goes here? South. Yep, south attracts north, and north attracts south. So is the board a north or a south pole? Well, it's neither, remember? It's paramagnetic. So when I bring the north pole of this magnet close to the board, what happens is these magnetic domains flip so that their south pole is facing it. Basically, you can think of it this way. The north pole of this magnet repels the north pole of the magnetic domains in here, so they all flip, and now it's a south pole, so it sticks. Good? So what happens with north and north? Repel. North, let's write this down. I'm going to erase this so I can start. People like it when I write things down in order. I have a real tendency to just like cram it in whatever blank spot there is on the board, but I know it's better if I write in order. So north and north, what do they do? Repel. South and south? Repel.
North and south attract.
North and south attract. North and south attract. And then obviously also, as Peyton says, south and north attract too. Opposites attract. Opposites attract. That was true for electricity. Negative charges attract positive charges. And it's also true for magnets. North poles attract south poles. This is the basics of what? No, just magnetism. Now let's combine them and talk about electromagnetism real quick because we have barely any time. So how do electricity and magnetism interact? Are you aware of a thing called a generator?
Yeah.
Okay, so how a generator works, and this has to do with electromagnetism. Basically, if we have, anytime electrons are moving, anytime electrons flow, what do we call that, by the way? The flow of electrons? Yeah. And specifically, is it an ocean current? No, electric current. Anytime there's electric current, a magnetic field is generated. Here's a wire. The electrons are flowing. We'll say this is supposed to be a battery. I'm supposed to make these different lengths, sorry. This is supposed to be a battery. We'll say the electrons are flowing this way. Flow of electrons. We use what's called the right-hand rule to tell which way the magnetic field is generated. So what you do for the right-hand rule, you take your right hand, even if you're left-handed, you take your right hand, so take your right hand, stop writing with your right hand, take your right hand, and you point it in the direction that the electrons are flowing with your thumb. Okay? Are you putting it in the direction that the electrons are flowing? And then the magnetic field goes in the direction your fingers are. So the magnetic field would be going in to the board and then coming out. I mean, it's hard to draw that on the board, but it would be going in and out. It's a three-dimensional thing. So if you have a wire and the electrons are flowing this way, the magnetic field goes the other way. So it generates a magnetic field in that direction. You can I'm aware of this because I have this super long HDMI cable, do you see it, that runs all the way from my desk to the Promethean board? So there's a lot of electrons that have to flow through there. It generates a magnetic field. If Mr. Jones downstairs, right below this, starts specifically the TIG welder, which generates an electromagnetic field, it screws up the electrons in my HDMI cord and it messes everything up for me. Because it's such a long cord that so much can go wrong, and that magnetic field that it generates with the TIG welder is strong enough that it ruins my HDMI. I mean, it doesn't ruin it, but it makes it momentarily out of action. It's when he starts it and when he stops it. While it's running, it's fine, and if it's not running, it's fine. But when he starts the TIG welder or when he stops the TIG welder, my HDMI cord cuts out. And for a split second, that'll say no signal, and then it'll unfreeze whatever I had, and you guys can watch my YouTube video with me. Yes?
So, like in a LAN cable, the power be flowing from the router to whatever you're hooked up to? Or from
Yeah, it depends, because there's more than just electricity flowing through a LAN cable. There's data in it, which it was generated with. I mean, the signal is by electrons, but it's a radio frequency too. So probably, yes. I think what you're getting at is, can like running your microwave oven or something else that generates a magnetic field mess up your internet connection? Definitely it can. Same thing with your cable television or whatever. But we use this by making a generator. So we take a spool of wire. Are you drawing a spool of wire like I am? And the electrons are going to flow, and so each spot of this is going to generate a magnetic field. If the electrons are flowing that way, the whole thing, every piece of wire is going to have a magnetic field going like this, isn't it?
Is this
And so
topspin, or is this
it's going like that. Whoop. Each wire is generating like that, and then on the other side, it's going this way, so it's generating like that. So both of them, if we do them both at the same time, one's going this way, putting a magnetic field that's basically down. The other one's going this way, making a magnetic field down. And so we have this wire, and we put a magnet in it, a permanent magnet we put inside of there. And we can, this little apparatus can be two things. If we make the magnet move, it generates electricity, making it a generator. Magnet moves, generator. Well, I should say, if we make the magnet move, it's a generator. We use like a turbine or something. Like if we have a hydroelectric power plant, a turbine is powered by the water. If we have a wind plant, the wind powers a turbine, which makes this magnet move. And when that magnet moves, it makes its own electric current in the wire, which is then transferred to the people's houses. But we use the exact same thing, and if the magnet, or if the current makes the magnet move, if the current makes the magnet move, current makes magnet move, what might happen then? If we supply electricity to this with a battery, with a battery or a power socket, and the magnet starts to move on its own, what might that be? It's another whole thing. It's not a generator this time. It's a, what's the thing that, no, what's the thing that takes electrical power and makes movement? Motor. Motor and generator are almost the exact opposite thing. They're both this design, but if we make the magnet move and it generates electricity, that's a generator. And if we give it electricity and it makes the magnet move, it's a motor. You'll have an assignment. That's the end of the discussion. Bye.